Okay, so we're still looking at galvanic cells, and we want to talk about what are the standard conditions under which galvanic cells operate. So remember all of those reactions in the table of standard electrode potentials, those redox reactions, they're reversible reactions, okay? They are equilibrium reactions, and we spent all of that time learning about Le Chatelier and equilibrium reactions so that we could apply it in this topic as well, okay? So if you want to get volts out of a cell to do work, your EMF is actually going to depend on the rate of the redox reaction, okay? So because the redox reaction is an equilibrium reaction, it can be influenced by concentration, temperature, or the pressure of a gas. Remember, we did all of those Rice table calculations and everything. So take your knowledge of reaction rate and equilibrium reactions and start thinking about it in terms of electrochemistry. So there are standard conditions for galvanic cells when you want to calculate the value of your cell, and the standard conditions are: your electrolyte must be in a concentration of 1 mole per cubic decimeter. It happens at basically room temperature, so standard temperature for an electrolytic cell is 298 Kelvin. Notice this is not the same standard temperature for everything in chemistry. Some things use 0 and some things use 25. This is one of the things that use 25. Okay, so pay attention, it's 298 Kelvin. And if you're using a gas, the gas must be at standard pressure, which is 1 atmosphere or 101,3 kilopascals. Remember, this standard pressure will be on your data sheet. Okay, so don't worry too much about remembering the standard gas pressure. Just go and read it off your data sheet, but it'll be 1 atmosphere pressure and then 25 degrees. Electrolytes 1 mole per cubic decimeter. Now you may have noticed in the middle of that table there was a hydrogen reaction, and you might be thinking to yourself, how do I get a hydrogen metal electrode? It's impossible. It's not impossible. We use a standard hydrogen electrode, okay? You need 2 half cells to measure electrode potential, and when you want to find out for an unknown substance, you measure it against what is called the standard hydrogen electrode, okay? And scientists decided that if we set up this hydrogen electrode under the correct conditions, it's going to have an electrode potential of 0 volts. So all of those voltage readings in that table are compared to the standard hydrogen electrode. But we can't be using hydrogen metal as an electrode because hello, there's no such thing, okay? So if you are using something like hydrogen or chlorine and you don't actually have metal, you will use platinum as the electrode because platinum is very unreactive and inert. So what you do is you put the platinum in to conduct the electricity and you surround it with like a little container of gas. You can sometimes use carbon as well, but they more commonly use platinum in industry and in really big labs. We would use carbon because like we don't have the money for platinum, okay? So platinum is what we call inert. It's not going to react with anything. So it's an inert electrode and it can conduct electricity. And carbon the same, it's not reactive and it can conduct electricity. So it is what we call an inert electrode. And if you lie on your bed and do nothing, I will call you inert as well, because remember, it also comes from the word inertia. And remember, a body doesn't change its motion if it's got inertia. So the electrode is sitting there doing nothing. So this is what it actually looks like. You would have, for instance, your cell. So here's copper metal and copper sulfate. Here's the salt bridge between the two. And then what you do is you get the conductor. Can you see here comes the conductor in here? And then here's a piece of platinum metal. And they encase the platinum metal in the special glass tube. And then they bubble hydrogen gas in the glass tube. So the hydrogen gas comes in here next to the piece of platinum, and it's hydrogen gas in contact with an acidic solution. Look here, 1 molar protons, and this would be 1 molar copper sulfate. So like for instance, if you put like nitric acid in here, you would have 1 molar nitric acid in here, and then the H plus is in solution and the H2 is coming in here. So it is the gas in equilibrium with its, or not in equilibrium, the gas in contact with its ion, and here the metal in contact with its ion. And like for instance, if you put this hydrogen with copper, you would get that 0.34 volts that's on the table that you can read on your table of standard reduction potentials. So if you put the platinum electrode in, it's in an acidic solution of protons of 1 mole per cubic decimeter. You can use hydrochloric acid or sulfuric acid, okay? But watch out if you use sulfuric acid, it's polyprotic. It's going to donate 2 protons, so it's half a mole of sulfuric acid to give you 1 molar protons. And they bubble the gas over the electrode at atmospheric pressure, and you keep the temperature at 25 degrees, and then your reaction at this electrode will be 2 protons plus 2 electrons go to hydrogen, or the reverse. The hydrogen goes to the protons. Okay, depending on obviously what's in your other half cell. Is it copper? Is it iron? Is it zinc? Is it lithium? That will determine the reading on your voltmeter and whether the forward reaction with the hydrogen is favored or the backward reaction. So here are the 2 half reactions. It can be either the anode or the cathode. Hydrogen goes to 2 protons plus 2 electrons at the anode, or 2 protons plus 2 electrons go to hydrogen gas at the cathode. Now you have to write this in its cell notation a little bit differently. Okay, remember the salt bridge is like your mirror, and so from the mirror working to the left, if it's the anode, if it's the hydrogen going to the protons at the anode, here's my salt bridge. Here's my protons in aqueous solution at 1 mole per cubic decimeter. Here's my hydrogen gas at a pressure of 1 atmosphere. And then can you see, instead of my normal cell notation, which only had 1 vertical line, I've got 2 vertical lines, and the platinum metal is right on the edge. Okay, the platinum's always on the outside edge. So this is the one for oxidation, platinum, hydrogen, proton, salt bridge. If it were, for instance, coupled with something else where it acted as the cathode, it goes salt bridge. Remember, this is on the right, anode left, cathode right. Salt bridge, proton, hydrogen, platinum solid on the outside. Okay, try to remember your state symbols in here. They make your answer more complete. They're not vital, but they should be there. So if you mix something with a hydrogen electrode, if the EO cell is positive, then the metal ion gets reduced. If the EO cell is negative, the metal will be oxidized. Remember this copper zinc thing? It's plus 0.34 on the copper 2 plus and minus 0.76 on the zinc. So then you would write the platinum half cell with a hydrogen anode here for this first reaction and a copper cathode, and on this one zinc would be the anode and hydrogen would be the cathode. Okay, remember we're going to use these values to find this formula from the data sheet to find the value. Remember again, if you find EO cell, you have to write out the formula EO cell equals EO reduction minus EO oxidation, or EO cell equals EO cathode minus EO anode. Make sure you write out the whole word. Do not use abbreviations. So we will use these reactions here to predict cell potential. Okay, have a look at your substances that you're given. So what you do is you look at your reaction and they tell you what you've got in there. You look at your table of standard reduction potentials, pick which is the reducing agent, get the value, that's for the anode. Pick which is the oxidizing agent, this is the cathode. Write out the reaction, and then if EO cell is greater than 0, the reaction is positive. Remember, the anode can quite often be negative because it's the oxidizing agent, and a minus makes a plus. So the last part of this topic, okay, is what goes on with the equilibrium with these cells. Remember, we've just said we have to put everything in a very, very specific concentration and a very specific temperature and pressure because it's an equilibrium reaction. So remember, with equilibrium reactions, you can favor the forward reaction or favor the backward reaction. Okay, so as you're doing this, zinc plus copper ions goes to zinc ions plus copper ions, if we consider this our galvanic cell. As the copper ions are going to copper metal, they are continually taking copper ions out of solution, and on this side zinc ions are continually going into solution. And so remember, the salt bridge helps even out the charge, but the salt bridge is not going to do anything about which ions are in there. So for instance here, this side you're going to keep churning out zinc ions and they're going to keep going into the salt bridge. But on the other side of the salt bridge, they're going to shunt out sodium ions into the copper 2+. So you started out with only copper 2+ in here, and then as the cell goes along, whatever's in your salt bridge ends up in this solution. So on the one side your copper ion concentration drops, and on the other side your your zinc ion concentration increases. Okay, and the salt bridge is only evening out the charge, it's not changing the actual ions. So the moment something's got a decrease in concentration, its reaction will decrease. Okay, and then if the other one's got a concentration that increases, then the other reaction will be favored. Okay, so decreasing concentration decreases reaction rate. It's an equilibrium reaction, so you can favor the forward or the backward reaction. So the moment you favor a reaction and the flow of electrons changes, you're going to change the current. And if you decrease the flow of electrons, then the current will decrease. So usually what happens with these is the current eventually winds down to 0. Okay, because initially in any galvanic cell, the forward reaction is favored. But for instance, as time goes on and you use up all your copper 2+ ions, they're all converted to copper metal. There's no more copper 2+ ions, so the copper 2+ plus 2 electrons reaction is not favored, and eventually the copper will want to go back into solution again. Okay, when the reverse reaction is favored. And when you've got dynamic equilibrium, the forward and reverse reactions are going at the same rate, and the battery goes flat and your cell potential drops to nothing. So the moment you've got both forward and backward reactions, your battery starts, your voltmeter starts recording a lower voltage. And this is exactly what goes on with the chemicals in a battery as your battery goes flat. And eventually, in your real life battery, you've used up all your electrolytes and you throw the battery away because you can't exactly open it to put more electrolytes in. With a rechargeable battery, you put electrical energy back in to reverse the chemical reaction, so you can start over the next day with your cell phone. And that is the end of electrochemistry, but you need to go practice the questions. The one thing I want to say to you as well with potential difference in equilibrium, remember that if you form solid salts, if you put something in that forms a precipitate, for instance, like if you put silver nitrate into a chloride solution, remember you immediately get solid silver chloride. It's one of your grade 10 reactions in aqueous solution. If you are then putting something in that takes an ion out of solution and the ion was taking part in the reaction, you're going to have to apply Le Chatelier to it. So in some cases you can actually increase the voltage by adding something that causes a precipitation reaction, and if you add it to the wrong half cell, you can either increase or decrease the reaction depending. So just pay attention, be aware that forming a precipitate in the middle of this is also going to affect your cell reaction.